So I had a meeting with software and hardware people. So what I wanted to do was to interrupt the astronauts to tell them there's an emergency so they'd stop doing what they're doing. So they said it can't be done. I said, why not? So I came back with a solution the next day.
History is often taught as a chronicle of hardware milestones. The clatter of the Industrial Revolution's gears, the humming vacuum tubes of the 1940s, and the silent silicon of the modern era. But hardware is just a cold, dormant body. A computer without code is like an instrument without a hand. It has the potential for music, but no voice. The soul of computing is the logic that brings it to life. Today, we are looking at three architects of the invisible. These women didn't just inhabit the world of computer science. They invented the very concept of software at times when the world didn't even exist. We begin in the 1830s with Ada Lovelace, a woman whose life was a battleground between the cold rigor of mathematics and the volatile fire of romantic poetry. Ada was the only legitimate child of Lord Byron, the mad, bad and dangerous to know. Her mother, Lady Annabel Milbank, was a gifted mathematician herself, whom Byron mocked as the princess of parallelograms. After their marriage collapsed in a cloud of scandal, Annabel became obsessed with curing Ada of any potential poetic madness. She subjected the girl to brutal education in logic and math starting at age 4, hoping it would act as a mental straitjacket. Ada wasn't allowed to see a portrait of her father until she was 20, but you cannot suppress a mind like Ada's. It simply finds new ways to bloom. As a child, she didn't just solve equations, she studied the anatomy of birds to design a flying machine. In 1828, at just 12 years old, she produced a book called Flyology, illustrating a steam-powered winged horse. She wrote to her mother, "I have got a scheme to make a thing in the form of a horse with a steam engine in the inside, so contrived as to move an immense pair of wings, to allow it to soar in the air." This was the poetical science she would champion for the rest of her life. The idea that imagination is the most essential tool for a mathematician. In 1833, she met Charles Babbage at a party. He was showing off a small fragment of his difference engine. Most guests saw a curiosity, but Ada, she saw a destiny. Babbage was designing the analytical engine. To him, this was a massive brass calculator meant to eliminate human error in the tight tables. To Ada, it was a gateway to a new reality. In her famous 1843 notes on the machine, which were 3 times longer than the paper she was translating, she went far beyond calculation. In Note G, she outlined the first complex algorithm, a method for the machine to calculate binary numbers. While Babbage had sketched out simpler programs earlier, Ada's algorithm was the first published and the first to demonstrate the complex logic of loops and subroutines that would look familiar to any programmer today. Lovelace was the first to realize that the machine wasn't limited to numbers. She famously wrote that the analytical engine weaves algebraic patterns just as the jacquard looms weave flowers and leaves. She understood that if you could represent music, art, or language as symbols, a machine could process the entire world. She saw universal computation a century before Alan Turing. Her later years were a dark, brilliant tragedy. She attempted to create a calculus of the nervous system to map how the brain creates thoughts, a precursor to modern neural networks. In her final years, she became entangled in a secret gambling circle, attempting to use mathematical models to beat the horse tracks. Contrary to legend, there is no evidence she did this with Babbage. In fact, she lost a significant portion of the family fortune on her own. She died of uterine cancer at 36. She requested to be buried next to the father she never knew, finally reuniting the poetry and the math in the silence of the Byron family vault. If Ada was the prophet, Grace Hopper was the general who turned prophecy into reality. By 1943, the world was at war, and Hopper a math professor with a PhD from Yale, wanted to fight. The Navy rejected her for being too old at 37 and too small, but she secured a waiver and was sent to Harvard to work on the Mark I, a 5-ton machine held together by 500 miles of wire that sounded like a room full of knitting needles when it ran. Grace was famously unorthodox. She kept a clock in her office that ran backward to remind her team that the most dangerous phrase in the language is, "We have always done it this way." She was known to dismantle every piece of technology she could get her hands on. As a child, she took apart 7 alarm clocks before her mother realized what was happening. Hopper is often credited with coining the term bug, but the term had actually been used by others, including Thomas Edison, well, for decades to describe the technical glitches. However, Grace is responsible for the most famous bug in history. In September 1947, while working on the Mark II, her team found a literal moth trapped in Relay 70, panel F. They tapped the moth into the logbook, noting it was the first actual case of bug being found. I think we can say that her true scientific revolution was the invention of the compiler. In the early days, programming meant manually writing binary, endless strings of ones and zeros. You saw it in channel many times. It was machine-centric thinking. Grace argued that humans should talk to machines in English. Her colleagues thought she was delusional, insisting computers were arithmetic devices, not symbolic processors. She ignored them. "It's much easier to apologize than it is to get permission," she said. She built the A0 compiler, which translated human-readable commands into machine code. Grace also fought for the portability of code. Before her, a program written for one machine was useless on another. She helped create COBOL, the first language that could run across different hardware architectures. She became a media icon, appearing on 60 Minutes and carrying nanoseconds in her pocket, which was 11.8-inch pieces of wire representing the maximum distance light travels in 1/billionth of a second. She used them to explain to stubborn admirals why satellite signals had a lag, physically demonstrating the limits of the speed of light.
Now what I wanted when I asked for a nanosecond was, I wanted a piece of wire which would represent the maximum distance that electricity could travel in a billionth of a second. Now, of course, it wouldn't really be through wire. It'd be out in space, the velocity of light. So if you start with the velocity of light and use your friendly computer, you'll discover that a nanosecond is 11.8 inches long, the maximum limiting distance that electricity can travel in a billionth of a second.
She retired from the Navy at 79 as a Rear Admiral, leaving behind a world where talking to a computer was no longer a fantasy, but a standard. Finally, we reached the high-stakes, thick-clock thriller of the 1960s space race. Margaret Hamilton was a young mother and self-taught coder at MIT's Instrumentation Laboratory. At the time, software was looked down upon by hard engineers who built the rockets and engines. Margaret coined the term software engineering specifically to demand respect for her craft. She wanted to give it the same weight as civil or mechanical engineering. Margaret often brought her daughter Lauren to the lab on weekends. While Lauren played with a simulator of the Apollo command module, the child accidentally pushed a button that crashed the system. Margaret realized an astronaut could do the same in flight. She wanted to write a code to prevent this user error, but NASA management laughed, saying astronauts are trained never to make mistakes. They refused to let her add an automated software block to the system. Margaret wanted to add a code block to prevent this, but NASA said no. So she did the only thing a developer can do when management ignores a bug. She put a warning in the manual and prepared Plan B. On Apollo 8, Jim Lovell made that exact mistake, selecting P01 while in deep space, wiping the navigation data the ship needed to find its way home.
Well, wouldn't you know, after I was able to get that in, because it becomes part of the specs at that point, or requirements, whichever, they did it. They selected P01 during flight, and that was the Apollo 8. There were 3 of us, I remember. going through it, trying to find out what happened. I said, it's the Lauren bug. I know it's the Lauren bug. This is exactly what happened. So anyway, it was the Lauren bug.
Because Margaret had anticipated this impossible error, she and her team at MIT recognized the problem instantly. They spent 9 hours on the ground calculating new navigation coordinates to re-upload to the ship. Her persistence and foresight, rather than an automated fix, were the only reason the mission wasn't lost in the void. It is the ultimate "I told you so" in the history of computer science.
After that, they said, yes, Margaret, you can put that change in there. So it did get in there for the very next mission.
But her greatest legacy is the 12:02 alarm on Apollo 11. 3 minutes before landing on the moon, the computer's CPU was slammed with around 14% duty cycle overhead from a faulty radar switch. In any other system, this would cause a total crash or freeze.
So I had a meeting with software and hardware people. So what I wanted to do was to interrupt the astronauts to tell them there's an emergency so they'd stop doing what they're doing. So they said it can't be done. I said, why not? So I came back with a solution the next day.
Margaret had designed the executive software with priority scheduling. She built a system to be asynchronous. It could recognize that it was being overwhelmed, drop low priority background tasks, and focus 100% of its power on the landing thrusters and the steering. As the world held its breath and Neil Armstrong looked for a landing spot, Margaret's code was performing digital triage, making a split-second executive decisions to prioritize human life over data processing. There is a famous photo of Margaret standing next to the printed source code for the Apollo guidance computer. The stack of paper is as tall as she is. Every line of that stack was hand-woven into core rope memory by little old ladies who literally threaded wires through magnetic cores to create the ones and zeros. Margaret was the architect of that weave. From the poetic intuition of a Victorian countess to the bold compilers of a Navy Admiral and the rock-solid logic of a NASA pioneer, these women didn't just help build computer science, they gave it a soul. They proved that the machine's brilliance is really just the reflection of the human mind behind it. Ada Lovelace saw the dream. Grace Hopper built the bridge. Margaret Hamilton made sure we landed safely. If you want to dig deeper, try this video where I talk about the history of programming. That will be all for today. Thanks for watching. If you want to see more in the future, don't forget to hit the subscribe button and ciao!